Sand, a material seemingly worthless beneath our feet, is actually the primary source of the digital revolution that powers our modern world today in this era. From these simple grains of silicon, humanity has managed to engineer artificial brains containing billions of transistors that process information at the speed of light. How can raw silicon transform into the most complex devices ever made? Welcome to an incredible journey deep into the fascinating world of the ultra-microscopic. Inside every smartphone and computer lies a hidden masterpiece of engineering that we often take for granted while using our favorite digital applications and tools. To understand this scale, we must look closer than the human eye can see, comparing the physical world we know to the miniature realm of semiconductors. As this tiny square of material is more powerful than the room-sized computers of the past, holding the key to our global communication and data processing networks. As we peel back the layers of our electronics, we find the mysterious heart of the machine, where electricity flows through complex paths of pure silicon. Let us explore the process of turning common sand into the heart of the digital age, a journey involving extreme heat and incredible scientific precision. The transformation begins in giant industrial plants, where raw materials are processed through extreme chemical reactions to isolate the essential element we need for chips. Inside these massive furnaces, the temperature reaches levels higher than molten lava, breaking the chemical bonds of quartz sand to extract the metallurgical-grade silicon. At 2000 degrees Celsius, the sand melts into a liquid state, allowing scientists to begin the rigorous process of purification for high-tech semiconductor applications. Every impurity must be removed, as the semiconductor industry requires a level of purity that is almost impossible to imagine in any other manufacturing sector. Using the Czochralski method, a single seed crystal is dipped into the molten vat to begin the growth of a perfect, uniform single crystal silicon ingot. As the ingot rises, it cools and solidifies into a massive cylinder of pure silicon, representing the perfect atomic arrangement required for advanced electronic circuits. This slow and careful rotation ensures that the entire structure remains consistent, preventing any defects that could ruin the final performance of the microchips later. The result is a monolithic crystal that serves as the foundation for the entire digital world, waiting to be sliced into many thousands of individual wafers. Technicians must ensure that the crystal is flawless, as even a single atom out of place can cause failure in the microscopic circuits being built. To reach the standard of 9/9 purity, the material undergoes multiple stages of chemical refining until it is the cleanest substance on the planet. This is the true essence of technology, taking raw earth and refining it into a state of absolute perfection that allows for modern computational power. Now we enter the mechanical phase, where the giant silicon crystal will be divided into the thin plates that we call wafers for further processing. Using diamond-coated saws, the machines slice the ingot with extreme precision, creating slices that are thinner than a human hair but strong enough to process. The cutting process must be perfectly controlled to avoid cracking the brittle silicon, using constant water cooling to manage the heat generated by the friction. Each of these wafers will eventually become the base for hundreds or even thousands of individual microprocessors used in everything from cars to supercomputers. After slicing, as the wafers are rough and must be polished using a chemical slurry that grinds the surface down to an incredible level of flatness. The goal is a surface so flat that any variation is measured in atoms, providing a perfect mirror for the light-based lithography process that follows next. Sophisticated sensors scan every millimeter of the wafer to detect even the smallest scratches or dust particles that could interfere with the delicate circuit patterns. With the foundations laid and the surfaces prepared, these wafers are now ready to be transported into the most controlled environments on the entire planet. We now enter the clean room, an environment where the air is filtered to be thousands of times cleaner than the air in a typical hospital. Workers must wear specialized protective gear to prevent human skin cells or hair from contaminating the wafers, as one speck of dust can destroy circuits. Robotic systems handle the movement of wafers in sealed containers, and ensuring that the environment remains perfectly stable throughout the many weeks of the manufacturing process. The labs are lit with a distinct yellow hue because the photoresist chemicals on the wafers would react and harden if exposed to normal white light. First, the wafer is coated with a light-sensitive polymer called photoresist, which is spread into an extremely thin and even layer by rapid centrifugal force. This coating must be perfectly uniform across the entire surface, acting like the film in a camera that will soon capture the image of circuits. The heart of the facility is the EUV lithography machine, a multi-million-dollar piece of equipment that uses light to print patterns at the nanoscale level. Extreme ultraviolet light has a wavelength so short that it can define features only a few nanometers wide, pushing the boundaries of what is physically possible. The light passes through a photomask, which contains the blueprint of the chip and is focused by the world's most precise mirrors onto the wafer. Every pulse of light transfers a portion of the complex design, repeating this process hundreds of times across the wafer to create many identical microchips. We are now drawing with light, creating structures so small that millions of them could fit on the head of a single pin without touching. Each chip contains billions of transistors, which act as tiny switches that control the flow of electricity to perform complex logic and memory functions today. The entire process is monitored with extreme care, as even the slightest vibration or temperature change could cause the patterns to become misaligned and useless. Once exposed, the wafer moves to the development stage, where chemicals wash away the parts of the photoresist that were hit by the ultraviolet light. The result is a physical map of the chip's architecture, etched into the light-sensitive layer and ready to be carved into the silicon itself very soon. In the ion implantation stage, we fire high-energy ions into the silicon to change its electrical conductivity in very specific and highly controlled areas. By carefully doping the silicon with different elements, we create the positive and negative regions that allow transistors to function as electronic switches. Next, the wafer enters a chemical vapor deposition chamber where layers of insulating or conducting materials are grown one single atom at a time. These layers are essential to keep the different parts of the circuit from short-circuiting, providing the structural insulation needed for such high-density electronics. The chemistry must be perfectly balanced, using exotic gases that react only when they touch the heated surface of the rotating silicon wafer. This is the ultimate in precision manufacturing. On building three-dimensional structures at a scale where we are literally manipulating the building blocks of matter. To remove unwanted material, the wafer is subjected to plasma etching, which uses ionized gas to eat away the areas not protected by the photoresist. The etching process creates the deep trenches and vertical walls that form the modern FinFET transistors, the three-dimensional structures used in today's fastest chips. These vertical structures provide better control over the flow of electrons, allowing chips to run faster while using significantly less power than older designs. As we add more layers, the chip begins to resemble a massive city with multiple levels of roads and tunnels, all packed into a tiny space. The precision required is staggering. If these gates were even slightly misaligned, the entire processor could fail to work or consume too much energy. As this is a network of information pathways more complex than any transportation system on Earth, designed to move data with almost zero resistance. In the background, massive support systems maintain the vacuum and pressure levels needed for these delicate chemical and physical reactions to occur successfully. The technology used here borrows from particle physics, using small accelerators to ensure that ions reach the exact depth needed within the silicon crystal. Each step brings us closer to the final product, turning a simple slice of sand into a functional piece of advanced digital technology and logic. To connect the billions of transistors, we use electroplating to fill the etched trenches with highly conductive copper, creating the chip's internal wiring system. These layers of metal act like the blood vessels of the chip, carrying the electrical signals that represent the binary code of our digital data. Modern chips can have over 15 layers of metal wiring, all perfectly aligned to connect the microscopic transistors in the correct logical sequence. Once the fabrication is complete, every single chip on the wafer must be tested using a probe card that checks for electrical connectivity and logic. The machine sends rapid electrical pulses through the needles to verify that every transistor and connection is working exactly as the designers intended. The speed of testing is incredible, as the systems can verify millions of circuit paths in just a fraction of a second for each chip. Any chips that fail the rigorous tests are marked, ensuring that only the most perfect and reliable components make it into our final consumer devices. This data is fed back into the manufacturing system to improve the process and increase the yield of good chips from every silicon wafer produced. Next, the wafer is cut into individual pieces called dies, using a laser or a diamond saw, separating the collective work into independent units. Each tiny rectangle is now a complete processor, but it is still very fragile and needs to be protected from the outside world's harsh conditions. Robotic arms move with incredible speed and precision, placing each die into its own protective package where it will be securely connected and sealed. The package provides the interface between the microscopic world of the chip and the larger world of the circuit board inside your electronic devices. Tiny gold wires, thinner than a human hair, are bonded to the chip to provide the electrical connections that will power the device in the future. Finally, the chip is encapsulated in a hard plastic or ceramic shell, acting as a suit of armor against heat, moisture, and physical impact. With the logo etched on its surface, the journey from a simple grain of sand to a high-performance computer processor is now officially complete. From this facility, these chips will travel across the globe to be integrated into the tools that define our modern way of living and working. Semiconductors are the heart of the digital age, enabling everything from space exploration to the life-saving medical robots used by surgeons in modern hospitals. The journey of sand is the journey of human evolution, turning the common Earth into the infinite possibilities of our digital future. Thanks for watching.